All right, so in this video, we're going to do a random walk. So a lot of you probably heard the term before, especially in finance. Stock prices may follow a random walk and stuff like that. So um, random walk. This is an important thing to talk about before we get into the testing for unit root. So for a random walk, it's a time series where our YT is a sum of all the error terms. So let's say YT is equal to ET plus E of the day before plus all the way to the error term of 1 plus the initial value for our Y Y process. So a special case for a random walk is an AR or an autoregressive first order process. So for this, we'll say this is a very specific form for the AR model. So we'll say Y of t is equal to Y of the day before plus the error term. So in this specific case, our beta 1 is equal to 1. So this, and as you know, this is not a stable process. We talked about this earlier in the videos. This is not a stable autoregressive process. No, and again, remember that our error is IID, means 0, some variance. So this is not a stable autoregressive process. And because of y of t minus 1, this becomes our value for today would be equal to the error term for today, plus because beta is equal to 1, this is going to be equal to the error term before, plus the error term before that, plus all the way to the error term in the beginning, error 1, plus the initial value. And since the error term is IID with a mean 0, if we take the expected value for YT, all of these go to 0. All of the error terms go to 0, and that leaves us with the expected value for our initial value for Y. And this is true for all t equal to or greater than 1. So the expected value of a random walk doesn't depend on time. But of course, if we take the variance of this, if we take the variance, I'll write down here, if we do the variance of y, we have t many error terms, and each of those do have a variance. So if we do this, and that would mean that you do the variance for each of these, this would give you t many variances, t many variances of the error term. And then there are t many error terms. So this means that the variance of a random walk is a linear function of time. So it's linear because it's they're just multiplied. So it's not time squared. It's just multiplied by time. So this is linear in time. So variance of a random walk is linear in time. So let's suppose that you want to estimate the let's do an example. I'll clear all this so we have room. So let's suppose we want to estimate, let's say y of t plus k for some k. K could be any number, any integer. If we want to know the expected value for k many periods in the future, given y today, this is going to be equal to our the sum of all the error terms plus our y of t. So this goes back to the formula from before. It's just the sum of all those error terms. And because the error term is IID with the mean 0, this would mean that the expected value of y of t plus k is just going to be the expected value of YT, of time today. And this is, again, true for all k. This is true for all k equal to or greater than 1 in this case. So it's equal for all t and for all k. So remember that this random walk, this specific random walk, is an autoregressive first order AR process where our beta 1 is equal to 1. It's a unit root. So yt minus 1 plus our error term. So this is our unit root process. It's a very specific case of a random walk. So because, I won't write all that out, I won't write out all the words. So because our beta 1 is equal to 1, this is a unit root process. So don't confuse this with a highly persistent or a trending. So other types of models, but this is a unit root process. So this is important. And then so in the next video, we'll do a random walk with a drift, and then we'll talk about how to apply it to stock returns.